Leonhard Euler.
Hi everyone, today we will discuss about the graph in Euler circuits. Think of a various connection we experience in our lives. The friends connected in Facebook, cities connected by the roads, and gadgets connected by the internet. A branch of mathematics is called a graph theory. It illustrates and analyzes such as this is the example of a diagram. Friends that are connected on Facebook. Each dot represents the person and the line segment represent the connecting to two dots. The line segment, those are the people, our friends on Facebook. This is the line segment. This type of diagram is a graph. Note, take note that this is a different type of graph from a graph of a function. Now let's proceed to the definition of terms. There are two graphs. They have different contexts. Diagram A represents a valuable team, and the edge connecting against two vertices might mean that two teams play against each other during the current season. Diagram B represents the flight available on the particular airline between the selection of the cities. Each vertex represents cities and the edge connecting with two cities to each other connect. Means that there is a circuit flight between the two cities. These are the several examples of graph. The first one, this is a graph that has a 5 vertices. 1, 2, 3, 4, 5. 5 vertices. But no edge. It is not connected. Pag walay katong linya, dili siya connected graph. The second one, this is the connected graph that has a pair of multiple edge. Take note that twin edge cross in the center, there is no vertex unless a dot is drawn in the edge of considered to pass over each other without touching. Muna ang example number 2 pag this is the third graph. It is not connected. It is consist of two different sections. It also contains a loop. This one is a loop. Pasensya lang ninyo akong drawing kaya di ko kabalo. And the last one is a complete graph. This is the graph with the 5 vertices. Look at the example.
Welcome to a lesson on Euler paths and Euler circuits. An Euler path is a path that uses every edge in a graph with no repeats. Being a path, it does not have to return to the starting vertex. So looking at this first graph here, there's more than one way to form a Euler path. For example, if we start at vertex C, we could go from C to B, from B to A, from A to C, and C to D. This is an Euler path because we used every edge exactly one time with no repeats. To show the path, we can use arrows like we did here, or sometimes you'll see the edges numbered. For example, here we'd have 1, 2, 3, and 4. Just don't confuse this numbering with the weight of the edges. Looking at our second example here, if we start at vertex A, we could go from A to B, B to C, C to A to D, and D to C. So again, we started at A, ended at C, used all the edges exactly once. Or again, if we number these, we'd have 1, 2, 3, 4, and 5. Now an Euler's circuit is a circuit that uses every edge in a graph with no repeats. Being a circuit, that means it must start and end at the same vertex. So an Euler path does not have to start and end at the same vertex, but an Euler circuit does. So for example, if we start at, let's say, vertex B, we could go from B to A to E, back to B, to C, to D, to E, and back to B. Notice how we began at B, ended at B, and used each edge exactly once. So we'd have 1, 2, 3, 4, 5, 6, and 7. But not all graphs have Euler paths and Euler circuits, which leads us to Euler's path and circuit theorems. A graph will contain an Euler path if it contains, at most, 2 vertices of odd degree. A graph will contain an Euler circuit if all vertices have even degree. Notice how these theorems do not tell us how to find the Euler path or circuit, it just tells us if one exists. And just to review, remember the degree or valence of a vertex is the number of edges meeting at that vertex. Let's take a look at some more examples. We want to determine if each graph has an Euler path, and if it has one, we want to find an Euler path. So again, remember, we're first going to check to see if there are at most 2 vertices of odd degree. So looking at our first graph here, notice how vertex B has degree 2, so does vertex A, E, and D, but vertex C and F have degree 3. Notice how it does satisfy the requirement to have an Euler path. It has 2 vertices of odd degree, which is okay. So we can say the graph does have an Euler path, and now let's find one. So we want to start at a vertex and form a path that uses every edge exactly once. Let's say we try beginning at vertex B. We could go from vertex B to vertex A to vertex F, then vertex F to vertex E, E to D, D to C, and now we have a problem. If we go from C to F, we'll have to backtrack or use an edge more than once to get back to B. If we go to B now, we haven't used edge CF. So our current path is not going to give us an Euler path. So let's go ahead and try again. Remember, the theorem tells us if we have a path, it doesn't tell us how to find it. So now let's begin at vertex C. Let's try going to D, and then E, and then F. Let's go back up to C, and then from C to B, B to A, and A to F. I think we found it. We started at C and ended at F, and used each edge exactly one time. So again, we had 1, 2, 3, 4, 5, 6, 7, and we were done. So we can say the Euler path would be C, D, E, F, back to C, B, A, F. Now let's take a look at our second example. We'll begin by determining the degree of each vertex. So here we have degree 3, here we have degree 3, here we have degree 3. And actually we're done now because remember, we can have at most 2 vertices of odd degree. So we can stop here and say the graph does not have an Euler path. Now let's revisit Euler circuits. A graph will contain an Euler circuit if all vertices have even degree. We want to determine if each graph has an Euler circuit, and if it has one, we want to find an Euler circuit. We'll begin by determining the degree of each vertex. So we have degree 2, degree 2, degree 4, degree 4, degree 2, and degree 2. All the vertices have even degree, therefore this graph does have an Euler circuit. So now we'll find an Euler circuit. So we'll begin at one vertex, form a path using all edges exactly one time, returning to the starting vertex. So if we start at vertex C, let's go to vertex B, to A, to F, back to C, to D, to E, to F, and back to C. So we started at C, went to B, to A, to F, to C, to D, to E, to F, and back to C. So our Euler circuit. So the Euler circuit again is C, B, A, F, C, D, E, F, and back to C. And you may have noticed this Euler circuit is not unique. Looking at our second graph, we can quickly see that vertex B has degree 2, but vertex C has degree 3. As soon as we know a vertex has an odd degree, we can stop. The graph will not have an Euler circuit. Now you might be asking, why do we care if an Euler circuit exists? Think back to our police officer on patrol from a previous example. The police officer wanted to patrol a neighborhood on foot by walking as little as possible. The ideal situation would be a circuit that covers every street with no repeats, and that's an Euler circuit. Luckily, Euler solved the question of whether or not an Euler path or circuit will exist. So looking at our graph here, notice how vertices A, F, C, and D all have degree 2. Vertices B and E have degree 4. Because all the vertices have an even degree, we can easily determine this graph does have an Euler circuit, which we actually found by trial and error in a previous lesson. One possibility would be to start at E, to D, to C, to B, back to E, to F, to A, to B, and finally back to E. Again, the Euler circuit was to follow this path. 1, 2, 3, 4, 5, 6, 7, and 8. I hope you found this helpful.
In this presentation, we are going to look at weighted graphs as part of our graph theory series. Now, in particular, what we're going to do here is to write the adjacency matrix for the following weighted graph. Okay, so we have 6 vertices there. They are all have degree 3. And so what we're going to do is write out the adjacency matrix for these. And on the adjacency matrix, rather than the fact that they are connected or not connected, what we're going to do is the weighting. We're going to indicate the weighting of the the edge between each vertex. So V1, V2, V3, V4, V5, and V6. Not exactly necessary to put in the row names and column names of a adjacency matrix, but it actually just is helpful when you're just getting started. Again, V1, V2, V3, V4, V5, and V6. Okay, so let's look at vertex 1. It's not connected to itself. Okay, 0 there. It is connected to vertex 2, and therefore we're going to put a 2 there because the weighting of that edge is 2. So it is the entry for the adjacency matrix is 2. It's not connected to vertex 3, so we're going to have a 0 there. Now, it is connected to vertex 4, and you have to just be a little bit careful when you're reading the graph that this edge here is vertex 4. So I'm just going to sort of indicate which of these are connected to which. So that 3 is there is connected to that edge, that 3 there is connected to that edge, and that 4 there is connected to that edge. So that is the weighting from V1 to V4. So there's a 4 there. So the next thing we're going to do is it connected to V5? No, it's not. What about V6? Yes, it is connected to V6 with a weighting of 8. Okay. Now we've seen previously that V1 and V2 are connected to each other with the edge of that has weight 2. And that actually works in reverse. So V2 is actually connected to V1 the same way. Again, it's the one right up here up at the top. And in fact, they all are. So what I'm actually going to do right now, to save time, is I'm going to sort of write this row, the first row, along the first column, because there's a symmetric quality of what we're doing here. 0, 2, 0, 4, 0, 8. So as symmetric quality means if V1 is connected to V4, that means V4 is connected to V1. And if V5 is not connected to V1, V1 is not connected to V5, and so on. So we have the first one there for V2. So we're just going to work on the second row now here. And we have the first one for V2. It's also connected to V3. It's not connected to itself, so 0 there. And it is connected to V3 with this 5 here. So 5. It's not connected to V4, 0. It is connected to V5 with that edge of weighting 3, this one here. So that is a 3 and a 0. It's not connected to V6. And again, what we can do is write the second row along the second column. So we already have the first two entries there, so that we just have to complete it. 5, 0, 3, 0. And again, it's to do with the symmetric quality of an edge. If V1 is connected to V2, then V2 is connected to V1. So V3, we've already got it's not connected to V1. It is connected to V2 with degree 5, with an edge of weighting 5. It's not connected to itself. It's connected to V4 with an edge weighting of 7. It is not connected to V5, but it is connected to V6 with an edge with weight 3. And once again, write that along the bottom, or along the column, the third column. Things start to work very quickly once you recognize that symmetry quality. Now we're going to look at V4. It's connected to V1 with a weighting of 4, V2 with no edge. It's connected to V3 with a weighting of 7. It's not connected to itself. It is connected to V5, so we have a 2 there because the weighting is 2, and it's not connected to V6. Once again, 2 and 0. Now V5, it's not connected to V1. It is connected to V2 with a weighting of 3. Not connected to V3. It is connected to V4 with a weighting of 2. It's not connected to itself, so we're going to put in a 0 here. And finally, it's connected to V6 with a weighting of 6. And again, we'll put in 6 here. And finally, V6, the only thing we have to do now is V6 connected to itself. No, it's not. So that is the adjacency matrix for the weighted graph. What I'm going to do now is just sort of present the answers a bit more clearly. There is the adjacency matrix there with the proper notation for the A of G as well. So that's what the answer should look like. Okay, and in terms of proper presentation, the V1, V2 thing, I don't know, at the top of the last slide was just to sort of help guide the eye. Those column names and row names, they were just to help guide the eye. They're not actually really necessary. Okay, that ends our presentation.